We're going to get started today with solving the last problem. So question 4 on this exam, ENGR110 practice exam. So question number 4. So this is dealing with the relaxation frequencies of polymeric and biomaterials. So I really like this question. Hopefully if you've taken Engineering 45, this graph should look very familiar. So this is a plot of basically a result of, dynamic mechanical testing. So typically for, we deal with linear elastic materials. We're going to see that when we get to kind of lecture 10 in mechanics. But if you're working with polymeric materials, biomaterials, gels, even some glasses, those materials don't behave as a linear elastic material. Instead, they behave as a viscoelastic material. So viscoelastic material. So viscoelastic material has two responses, a viscous response, so kind of like a liquid, it's going to flow, and elastic response where there's an instantaneous elastic, mechanical response. So in visco and elastic. So the cool part about the dynamic mechanical testing is that you measure basically by applying some type of sinusoidal varying stress. So kind of like this. You can measure a strain. And from that, there's definitely some calculations that go into this, but you're able to measure essentially the shear modulus, G double prime, which is your loss modulus, and your storage modulus, G prime. Your G double prime is essentially your viscous response, and your G prime is your elastic response. So, depending on the magnitude of these two kind of G prime, G double prime, your material will be able to behave like a viscous material or an elastic material. So on this side of the curve, when we're applying essentially a stress or strain at low frequencies, you're allowing that polymer or that kind of biomaterial to kind of reconfigure and rearrange its structure and respond essentially to that stress. So it's going to flow. So at low frequencies, it's going to behave like a viscous material. And you can see that because the red curve is larger than the blue curve. On this side of the curve here, the blue curve now dominates. Again, higher frequencies, you're not allowing that polymer to kind of rearrange, so you're kind of just going to pull on the bonds, you're not allowing it to kind of flow. This will be your elastic response. And this crossover point here, this is the kind of characteristic relaxation time of your polymer chain. So if you take 1 over the frequency, you'll figure out what's the time that that polymer requires for that polymer, that biomaterial to kind of reconfigure and reorganize itself. So this is what we're interested here in this problem. So you don't have to be an expert in viscoelastic material to do well on this problem. So let's go ahead and figure out, all right, let's analyze this signal. So, sorry, once I erase, you all know that it takes me a while to completely erase my screen. There's probably a function that says clear all drawings, but I do not know how to do that. Anyways, so let's look at what the problem's actually asking us. So polymer relaxation times can vary between 1 minute, 1 microsecond. We need to have a frequency resolution. Frequency resolution that could pop up. We know that our delta F must be 0.01 at least. 1 hertz, less than or equal to. For 3 options for my DAC, option A. So I'm going to start right in here. So for A, my maximum sampling rate is 1 million hertz. So my Fs max can be 1 times 10 to the 6. hertz. B, my Fs, so that is our that is our Fs, and we could capture 1 billion data points. So N equals 1 times 10 to the 9. B, we have a maximum sample rate of 5 million hertz. 10 times 10 to the 6. And we can capture 100 million data points. So N is equal to 100 times 10 to the 6. And C, we could have a maximum sampling rate of 2 million hertz. And N can be, again, 1 billion data points. So the question now is, which DAC should I buy to capture my signal? Well, I'm not given. I need to find my F max, and then what are the signals that I need, or the frequencies that I need to measure in this signal? Well, we're given time, so we need to convert that to frequencies. So for 1 minute, my F for that signal is just going to be 1 divided by 60 hertz. And my maximum frequency of my signal is going to be 1 over that microsecond. 1 microsecond is 1 times 10 to the minus 6. So my F max is going to be equal to 1 times 10 to the 6 hertz. That's it. We have our F max. we have our F. Now, is our F, we need to have a frequency resolution of at least delta F is less than or equal to 0.01 hertz. So that corresponds to F over 1 over 100. So we have an issue here, right? So we can't choose this kind of 1 over 60. We need to choose something smaller than this for basically, for this, our delta F. Our delta F has to be less than or equal to this, but we need to still have integer multiples so we could kind of capture this. So we'll kind of come to that in a second. But let's deal with signal aliasing first. So our F max is 1 times 10 to the 6. So which of these options are going to allow us to not alias our signal? Will 1 work? Will A work? What's our rule? To not alias, we need to make sure that Fs is basically greater than 2 times F max, right? So 2 times F max, C, will it work? No, it's not greater than. It's equal to, but you'll still have aliasing. 1A, that's not going to work at all. So B is the only sample that is going to work to not alias our signal. So now we have to figure out, okay, what is, can we get this value to not get spectral leakage? So I'm going to flip my screen real quick and go to Mathematica because I don't want to do this math by hand. So, excuse me. Screen flip right there. So my Mathematica crashed in the last video. So let's continue on with that analysis. So, so our issue here is we need, this is the lowest frequency in our signal. So let's take a peek at that. This is our highest frequency in our signal, 1 times 10 to the 6th. The issue is we need our delta F to be less than or equal to 0.01. So we cannot use this value to be our delta F, but we can set delta F. Again, we just needed this to be, let me clear everything. Bad practice, Josh. You have to clear your notebook to make sure there's no hidden variables. So, but I can set my delta F to be 1 divided by 120, for example. Because that will be an integer multiple, and we'll see that in a second, and it will hit both of those values, right? Because we want to avoid spectral leakage. So we could prove this by delta F times what integer will give me 1 divided by 60, which is my lowest frequency, except you can't solve that, Josh. 1 divided by 60, solve for I, 2. And let's see if it hits a million as well. 1 times 10 to the 6th. Yep. So we need this many harmonics in order to hit that value. So delta F will hit both of those frequencies if we chose it to be 1 divided by 120. So now we have to figure out, again, we have to choose a sampling frequency that won't have aliasing, so it needs to be at least, it has to be greater than 2 times F max, because this is our F max. So it needs to be at least greater than 2 times F max, which is 2 times F max, which is 2 million hertz. So all we have to do now is solve and see, is our DAC capable of giving us these values? So looking back here, we already canceled out A and C. It's not going to work here. So instead, let's try and play around with B. So my B, I could sample up to 5 million hertz. So let's solve. I know that delta F is equal to Fs divided by big N. And I want to solve for big N. And I'm going to say, let's say I'm just going to do the max, just to be safe. I really don't want to alias my signal. So 5 times 10 to the 6th. This is going to require 6 times 10 to the, let's see, 1, 2, 3, 4, 5, 6, 7, 8. So it is going to take 600, 6 times 10 to the 8th, right? 1, 2, 3, 4, 5, 6, 7, 8. So 6 times 10 to the 8th data points. So can we capture that with, here, we're limited to n equals 100 times 10 to the 6th. So is that going to work? So 100 times 10 to the 6th is 1 times 10 to the 8th. So here we have 6 times 10 to the 8th. So we have a problem here, right? Let's reduce it to 3 million, for example. Still 3.6 times 10 to the 8th. How about even at 2 million, which exactly is, we'd alias our signal at this point, that's not going to work. So how about let's do 2 times 10 to the 6th, because we just need our sampling frequency. One of the requirements in this problem is that the sampling frequency can only be integer values. So let's just say 2 times 10 to the 6th plus 1. Get really, really tricky here. Let's see if we could just push the limits, but again, it's not going to be possible. But just to make sure. No, we still have an issue. So this DAC is not going to work. Unfortunately, the A or B or C could work, or actually would work, as long as we could, if our maximum sampling frequency was larger. So which DAC should you buy? None of these. All these are going to fail. So it's not going to work. So that's kind of the answer here. So again, a lot of these problems might not have an answer. Go through this analysis and you'll be fine. So B, what is the minimum sampling frequency, frequency resolution, number of points, and period required to properly capture the relaxation frequencies? So again, we've kind of already set this out here. So if you want the minimum sampling frequency, so we need at least, again, it has to be integer values. So the minimum would just be this. So Fs min would be here. So that's your minimum sampling frequency. Your minimum delta F, we've kind of already shown here in order to meet that requirement that we need a frequency resolution of at least this or less. That won't give us this kind of error here. This would be your minimum N. If this your minimum big N value, so that's what it's asking for. The minimum number of points, so that would be that value right here. If this is my Fs min, I know my delta T is just going to be 1 divided by Fs min. So that is my delta T value. I know I could calculate my period. T is equal to my big N times, so it would be this value right here. This value times delta T. It would be 120 seconds. So we've got minimum sampling frequency, done. Frequency resolution, done. Number of points, done. Period required, done. That's it. So again, attack these problems just like, again, deal with sampling frequency first, then see if you could basically get enough, or if spectral leakage is a problem, or if you can capture these signals, and then work from there. So, yeah, that's it. Last problem done. So hopefully you're ready now for the exam. If there's any questions, please let me know, and I'll see you guys a little bit later. Thanks. Bye.